you. Okay, last one from my side. This one is on higher order topological insulators, a form of topological crystalline insulators. And this is a rather recent subject. This lecture could have equally well been given by Andre, who pioneered this with this paper. And then also I got involved with this more recent paper, and a lot of people on this paper are actually here also. Frank, Ashley, Maya, Andre. Yeah. Okay, cool. So the basic idea is, can we sort of bring this bulk boundary correspondence of topological phases to a slightly different level? And so the simplest place to start again is our Suschrieffer-Heger model. And so you remember this was this dimerized chain. And we had this one end state that was dangling here. And that is in 1D, as you see. And now the question that I would like to ask is, if we have a two-dimensional system, could we have a situation where the bulk of the system is gapped, the edge is gapped, but we have a state at the corner that is gapless, like this end state of the Suschrieffer-Heger chain. So topological corner state. So and the point should be that this is a property of the bulk of the system. Of course, I can always engineer some one-dimensional system where there is some state here, so I can glue it to some bulk that is trivial. That's not the idea. The idea is I give you a bulk of a system, you compute something in the bulk, and then when I cut the system and make a corner, you can predict, you can tell me from the bulk, from looking at the bulk electronic structure, whether the corner will have such a topological mode. And so the way I'm gonna introduce that is that this corner mode is protected. Again, since we're talking about crystalline symmetries, is protected by a non-local symmetry, and that is the mirror symmetry that is given by the mirror reflection that goes through the corner. Okay. So let's just think about this dimerization picture from the Suschrieffer-Heger model, because it's really convenient, and see whether we can extend that to 2D. So if we have a lattice, and what we kind of want to do is we want to dimerize it in such a way that we passivate everything in the bulk and on the edges, and only that corner remains. So for example, we could think of making bonds here, right? And then all the edges are gone, and then maybe we can make some bonds here, and then everything in the bulk is gone, right? So you get the idea? Sorry. And the unit cell in this case would be containing 4 atoms, right? So unfortunately, this does. So it's certainly mirror symmetric, right? But it doesn't quite work, because if you think about these 4 sides here, what these bonds mean is basically a hopping integral, right? And then I think about it's like a little loop with 4 sides. So when I take a cosine band and I have 4 sides, then I have momentum at pi plus or minus pi half and 0, right? And then you see that the energy spectrum of this little 4 sides would be gapless. There are 2 states exactly at 0 energy, so that doesn't work. What we can do to change this is we can insert a flux here in this plaquette, a pi flux, and that shifts the energy eigenvalues exactly by half, right, between the 2. So now, if I put a pi flux in the plaquette, the 4 energy eigenvalues are these 4 crosses that I draw here. So now it's gapped. Okay. So when I put a pi flux in this little plaquette, the bulk is gapped. And that's exactly the model that was proposed in this paper. You put a pi flux on every plaquette, also on these ones. The difference is, however, that you have some dimerization in such a way that you have these strong bonds here that are between the unit cell, and within the unit cell, you have weak bonds, okay? And then you, from the fully dimerized picture, you already saw that there is this end mode somehow left over. But that's really just a sort of a sketch, so let's have a look how we can understand this from a more topological point of view. And I want to study this from, say, 3 different perspectives. So the first one is going to be, I'll look at the Suschrieffer-Heger-like structure. So first on the diagonal. So far I have not really talked about the mirror symmetry much that is here in the diagonal. So if I look at the diagonal, then the model really looks like, in this fully dimerized limit, let's say, it looks like a bunch of these plaquettes that are completely disconnected and have pi flux, right? And it goes on like this. And so the Hamiltonian that would describe such a pi flux plaquette here, if I label the sides like 1, 2, 3, and 4, then my Hamiltonian, there is a hopping from 1 to 2, and from 4 to 1. And then let me put, to make the pi flux, let me put a -1, then I hop from 1 to 4 or 4 to 1. And then the Hamiltonian looks like that. Okay, so that would be the Hamiltonian for one of these plaquettes. And the mirror symmetry for this object, so obviously sides 1 and 3 get interchanged by this mirror symmetry, so it would be something like this. And side 2 remains where it is. And then I need to make sure that this mirror symmetry is compatible with the pi flux. And that means that it's kind of combined with the gauge transformation that's taken care of by this minus sign when I act on side 4. So you can convince yourself that this mirror symmetry commutes with this Hamiltonian. Yes?
Why did you choose pi flux?
So for one, it's time reversal symmetric, and yeah, it's time reversal symmetric. That's a nice one. But what you actually want is that so the mirror symmetry is supposed to not change this flux, right, up to this gauge transformation, or combined with this gauge transformation. So when you put like a flux that's not pi, it will be flipped to minus the flux value, and pi flux has the convenience that pi and minus pi is the same thing. It's like a little magnetic field that's going through this, and then when you apply a mirror symmetry that's in the plane perpendicular, the magnetic field will be flipped. And this magnetic field, since we are on a lattice, is basically invariant under this operation, because it's just pi and minus, or modulo 2 pi only defined. So if I was to, so it's basically because it needs to be, it's like a spinful mirror symmetry, it's a mirror symmetry that has to be combined with a gauge transformation in order for this to be symmetry of the system. Because you see the Hamiltonian, the hoppings that I've chosen is 1, 1, 1, minus 1, right? So you would say, oh, this is not mirror symmetric, but the physics is mirror symmetric. It's only that the gauge breaks the mirror symmetry, and I have to correct for that with choosing this mirror symmetry, because the physical system is obviously mirror symmetric. Right. Okay, so now the point is that I can basically diagonalize the Hamiltonian. This mirror symmetry has eigenvalues plus and minus 1, and it's two eigenstates with eigenvalue plus 1 and 2 eigenstates with eigenvalue minus 1. And so if I diagonalize the Hamiltonian in the mirror basis, so I can sort of write H twiddle, let's say, and I diagonalize this. This is the part with mirror eigenvalue +1. This is the part with mirror eigenvalue -1. There's no off-diagonal elements. And if I do that, I get the following structure. And I should also say that in this whole process, I keep chiral symmetry C, which is, you could already almost guess what it is. It's diagonal 1, -1, 1, -1. Okay? And so what you now see is that this exactly looks like the fully dimerized Hamiltonian of an SSH chain, but in each mirror subspace, right? So it's like, this is of course the Hamiltonian that mediates the hopping, just within it, like this little thing. So in the SSH language, it would be the hopping inter the unit cells, right? So this, okay, well, the square root of 2 doesn't really matter, but so this promotes hopping between the unit cells, and it's the same thing in the plus and minus subspace, and so basically what we see is this like two SSH chains, okay, one in each. One in each mirror subspace. So you would think, well, then there should be two end states, maybe, right? Because that's what we thought about for the morning lectures. If we have two SSH chains, there should be one comes with each comes with one end state. But here, due to this corner geometry, you see that the bulk boundary correspondence is altered, right? So when I draw this these little rectangles, these little squares here, this rhombohedra, I draw these here, right? This one, and so forth. So the last unit cell, the way this corner terminates is that there's just one side sitting, one side of type 2 sitting here, say, and nothing else, right? So in this last unit cell, there's only this one side. So even though there's these two chains, there's only one end state that's sitting at the corner. And that has a definite mirror eigenvalue, as you can see, right? So the 2 is mirror eigenvalue plus, right? Okay, so that's the first way of seeing that there is an end state explicitly, and then there's some connection to SSH physics. But I think we can make it a little more explicit in the second way of doing things. And for that, I'll write down an actual Hamiltonian for this system. So we'll go to a momentum space, and the hoppings on these weak bonds I will have with strength 1, and the strong bonds will have strength lambda. And then the Hamiltonian for this thing, I'll first write it down, explain then. This is going to be... Okay, so this is how the Hamiltonian looks, but I have to explain you how the indices work. So the 4 sides in the unit cell, I label them by pairs 0, 0, 1, 1, 1, 0, 0, 1. And this is like an I and J index. Each of them can be 0 or 1. And then so the sigma are Pauli matrices acting on I, and the tau are Pauli matrices acting on J. Okay, so part of the terms we can immediately understand, right? So there is these one terms. They are the ones that are really mediating the hopping within the unit cell, right? And then everything else multiplies lambda, and that's how basically that's just how the helping between the unit cells turns out to be. So now this system is in the topological phase for lambda larger than 1. And for lambda equal to 1, obviously it's gapless. It's just some pi flux model on the square lattice, which is actually having Dirac cones. And for lambda less than 1, it's in the trivial phase. Right? So that's where all the orbitals are just hybridized within the unit cell. Okay, so in this representation, I can also write down the diagonal symmetry explicitly, and it's not super enlightening, but I'll just, for completeness, write it down so that you see there's no magic happening. It's a little bit complicated looking. It exchanges a few of these Pauli matrices, and that's why it has this a bit more richer structure. Okay, so this is the symmetry that sends, so this is this diagonal mirror symmetry, essentially. And now what I want to show you is that I want to basically show you the topological index of the system. And this topological index is defined on the mirror invariant line in momentum space, similar to what we had before with these mirror invariant planes for mirror Chern numbers and so forth. So this time the mirror invariant lines are these two, right? Like, I mean, if we think of both of these diagonal mirror symmetries, so there's this MXY, there's MXY bar, these mirror symmetries. So we want to compute an invariant on this line, okay? And so on this line, the Hamiltonian can be, so the eigenstates of the Hamiltonian are also eigenstates, can be chosen to be eigenstates of this mirror symmetry. And so I can write down this H tilde in momentum space on, if I choose Kx equal to K and Ky equal to K, so on this diagonal, and then it takes this form. There's 4 zeros here, and then this form where this Q plus minus is just a function that we have almost seen already today. So again, this is a decomposition into mirror subspaces. So this is the mirror subspace plus, and this is the mirror subspace minus. And the fact that then there's also the chiral symmetry, which basically makes this off diagonal. And this Q plus minus of K is equal to square root of 2 times 1 plus lambda times e to the minus plus I K. Okay. So have we seen this form before today, or with something very similar? Well, we have, because that is basically the Suschrieffer-Heger model, right? So this is basically exactly the off-diagonal component of the Suschrieffer-Heger Hamiltonian. And so what this Hamiltonian on the diagonal in K-space is really a Suschrieffer-Heger model in each mirror subspace. There is one subtlety, and that is this different sign here in the exponential. And so if I compute basically this winding number invariant, we call nu plus minus in these in these systems with charge conjugation symmetry or chiral symmetry, that you can always define it in terms of this Q. It's given by by this integral, well, trace of q plus minus partial k. Okay, so it's basically just a way. Here we don't even need the trace, it's just this thing. Then we find that this is plus or minus 1, this winding number. Maybe I should not call it nu because nu was in different units before. It's plus or minus 1 for the two subspaces, so it's opposite. So what does that tell me? Well, first of all, it tells me that if I sum the two up, I get 0. So there is no dipole moment or no polarization in this system, in this direction, no net polarization. But there is a sort of a mirror-graded number that I could define, right? I could say I'm interested in plus, minus, and minus over 2 or something. And that is now 1. And that's, of course, only defined because I have this mirror symmetry. And this is 1 for lambda larger than 0, larger than 1, and for lambda less than 1, this n is equal to 0. So then it's topologically trivial. Okay, so that would be a way to define a bulk topological index that guarantees, that's basically describing this phase and guarantees the existence of this corner mode. As long as these edges are gapped, of course, right? So when you manipulate them and make them accidentally gapless, then there's no well-defined corner mode, but the idea is that you look at the generic symmetry allowed edge termination, and generic terminations will be gapped, because there's nothing that prevents them from being gapped. Okay, that was number 2. And now the third look at a topology will be using Dirac Hamiltonians. So this Hamiltonian, when you look near the phase transition, you see that, so when lambda is nearly 1, you see that there is the phase transition happens by a gap closing at pi pi, so at this point in the Brillouin zone here. And so we can basically expand the Hamiltonian around this point. So this is third option. And so this is basically sort of Dirac picture. And so then the Hamiltonian, and we call it H Dirac, expanded around, so k is equal to pi pi plus this p. So the p is the k dot p Hamiltonian. Huh? So that is 1 minus lambda sigma 1 tau 0 plus 1 minus lambda sigma 2 tau 2 plus lambda times px sigma 2 tau 3 minus lambda py sigma 2 tau 1. Okay. So what do we see here? Well, maybe 1 minus lambda is a little bit, it's a small number, so let me just replace that by delta. Okay, let's call that delta. So what do we see here? What is this? It's a two-dimensional Hamiltonian. These two matrices anticommute. And this also anticommutes. This anticommutes. Everything anticommutes. Okay. So this is a 2D Dirac Hamiltonian with two mass terms. And these two mass terms are tuned to be equal. And why are they equal? It's because of this mirror symmetry. So mxy, or mxy bar, times sigma 1 tau 0 times mxy bar inverse turns out to be sigma 2 tau 2. So if I take this first term, apply the mirror symmetry, I get this second one. Okay, so we have a Dirac equation with two equal mass terms. And now let's see what we can do. We want to solve for this corner mode, and so we need to look at the corner geometry. And now we'll do a little bit of acrobatics. this Dirac equation. So, so this corner geometry, let's say my topological material occupies this quarter of space, okay? So here I have, let me now, so basically the idea is now that these masses have a spatial variation, yeah? And we want to see whether there's any topological bound states associated with this spatial variation. So in fact, let me write this even yet a little differently. I'll write this as two general mass terms that can vary in space. So this one is M1 and this one is M2. I'll call this M1 and M2. And so here in the bulk we have M1 equal to M2 equal to delta. And outside I also have M1 equal to M2 because of the mirror symmetry, but equal to minus delta. So that's the general trick in these sort of Dirac descriptions of topological systems, that to go to the trivial phase, we revert the sign of the mass, okay? And then we see what we got. Now the question that we have to decide on is, what do we do on these surfaces? And now this mirror symmetry is not on every given surface. It doesn't impose any restrictions, so I can choose the mass differently there. And I'll choose it, for example, M1 equal to not equal to 0 here, and M2 equal to 0 near the surface. And then the mirror symmetry flips the M1 and M2, right? And it maps, of course, this surface to the other surface. So when I choose this on that surface, the other surface has to have M1 equal to 0 and M2 not equal to 0, okay? And so what is happening here? Well, so suppose, I know that this is, since it's a Dirac Hamiltonian, everything is gapped away from this corner, right? So away, you know, if I go far away here, there's always some mass term, right? Everywhere, in any direction. So it's always a gapped system. The only question is it going to be gapped at this corner as well, or is there something interesting? And now I can carefully basically look at what I've constructed. So here I have two masses which are equal to delta. If I look at the space of M1 and M2, for example, I have two masses which are equal to delta. Out here I have two masses which are equal to minus delta, yeah? So I'm there. And then if I think about going, so on a circle here, around this, then here I have M1 not equal to 0, M2 equal to 0, so I went down here. And then, well, I go to this place. And on the other surface, I have M2 not equal to 0 and M1 equal to 0. So I go there, okay? So what I have done, if I go around this point, this corner, I have a winding in the masses, in these two masses, right? So spatially, there is a winding happening as I go far away from the corner around this point. And that is imposed by this mirror symmetry, because if I choose this like that, I have to have the opposite mass here. I mean, the M1 and M2 switched. Okay, and now, since I don't have that much time to explain this in all detail, I'll hope that you would allow me to modify this structure a little bit and optimize basically for a convenient analytical solution. And that can be done if I linearize this mass dependence in position space. And I want to do this in the following way. If I write, first of all, I will go to complex coordinates. So x plus iy is going to be called z. And then minus ipx plus py is equal to partial z bar. You can verify that if you want. And minus I P x plus by minus IPy is going to be partial set, and then, well, x minus Iy is z bar, right? So this is just a convenient notation. And I would like to choose the following. I would like to choose the following spatial dependence of the masses. I want to use m1 plus I m2 equal to z, or m1 minus I m2 equal to z bar. Okay. So what these masses do is basically they form a vortex in position space, essentially. And this is also a vortex. And why can I do that? Well, the point is everything here is gapped. The only point where something interesting could happen is at this corner. And if I now verify that with this choice of masses, I get a zero energy state at the corner because I have this an isolated zero energy state, right? Because I have this chiral symmetry, I can deform the Hamiltonian from the sort of physical the spatial dependence of the masses to this sort of idealized one, and nothing else can happen. Because it stays gapped everywhere except at this isolated point. So it turns out that this Hamiltonian here, this H Dirac, then goes into a Hamiltonian that looks like follows. So it has Z bar, partial Z bar, Z. And then the Hermitian conjugate down here. Oh, let me write down the Hermitian conjugate. Z bar minus partial Z minus partial Z bar. Okay, so that would be in some appropriately chosen basis. I can't go through all the details. Would be this Hamiltonian. And then the point is that there are actually two zero energy modes that this Hamiltonian can support. I can quickly write them down for you. So one is e to the minus z bar times 0, 0, 1, 1. And the second one is e to the z squared plus z bar squared times 1, 1, 0, 0. So basically there are zero energy modes of this block and of that block, but we also want, if we want the bound state, we also want that the modes are normalizable, and this guy here is not normalizable because of this weird dependence on z and z bar squared. So it's not normalizable. So we found this guy, and this is just a Gaussian, drop off in all directions. So we've found this guy as a unique zero energy solution. Well, that it's unique. You can sit down in peace and quiet and check. But this is a unique zero energy solution of this Hamiltonian, which sits at this corner. Okay. And again, this Hamiltonian doesn't look quite like this one here because I've chosen this sort of linear dependence on the masses. But now, I can, deform it into this one, into the physical one, just by doing manipulations that will not affect the fact that everything is gapped except for this one mode. And then again, we have chiral symmetry, so this mode is pinned by chiral symmetry to exactly zero energy. Okay? Okay, so I hope that was not too fast, but that should be the almost the end of the story in 2D. Let me make one more remark. And that is, if you take this system here, and that would be a fourth, it's like a bonus thing now. A fourth way to look at the topology is actually a rather important one, and the central one in Andre's paper. If you look at the Wilson loops, the Wilson loop spectrum of the system, what would happen? So this system, let's say we want to compute the Wilson loop in this direction, in the y direction. Okay. So what would you expect? How would the Wilson loop spectrum look like? We said that there is a correspondence between topological, like the boundary, right? And so the boundary spectrum and the Wilson loop spectrum. So is the boundary gapped or gapless? That's gapped. Okay, perfect. So we would also expect that the Wilson loop spectrum is gapped, right? And that's indeed true. So the Wilson loop spectrum, this is a 4-band model, right? So the Wilson loop spectrum, let's say theta as a function of this kx then. So this is for the y Wilson loop, say. It will have 2 bands, but there's nothing that topologically makes them stick together or anything, right? There's no degeneracies that are enforced, so it's gapped. But then you can take this again as a system that is describing a one-dimensional electronic structure, if you wish. So the Wilson loop, you can write it as e to the I times some Hamiltonian, some so-called Wilson loop Hamiltonian, and the question is, what is the electronic structure of this one-dimensional system? And it turns out that these bands are actually carrying, as a Suschrieffer-Hecker model, they are carrying half integer polarization. So they are one-dimensional. This is a one-dimensionally non-trivial band structure. Okay. So if you compute the Wilson loop of the Wilson loop, so the Wilson loop of this band structure, then you would get a non-trivial answer. You'd get a state at half. Okay. Has non-trivial band structure. Okay, that just as a side remark. Now, now I will go to 3D quickly, and that will be really simple. And I want to show you that these higher order topological insulators also exist in 3 dimensions. So I take this Hamiltonian that I have. I set lambda equal to 1 now for simplicity. And I want to interpolate between the trivial and the topological case, similar to what I did before with the Suschrieffer-Hecker model by adding another momentum. And the way I can interpolate is by basically just putting this cosine kz here. Yeah, and then we know that there is a phase transition basically at kz equal to pi over 2. At kz equal to 0, this will be in the topological phase. At kz equal to pi, it will be in the trivial phase. And to make sure that the thing stays gapped, I can put this sine kz times something that is anti-commuting with everything else, let's say sigma 3 times tau 0. Okay? So this way I've just created a simple model that has what phenomenology now? You can almost infer it just by inspection. So I'll draw this now for a system which has open boundary conditions in x and y direction, but periodic boundary conditions in the z direction. Okay, so it's like a nanowire or something that's running in the z direction. And so what is the spectrum? So there's one good quantum number, and that is kz, okay, that I want to keep as good quantum number. And so at kz equal to 0, I said I have this It's actually called the quadrupole insulator, this 2D higher order phase. And that has these 4 corner states. At each corner, there's one corner state. And then it has its bulk bands, right? And then Kz equal to pi, I have a trivial insulator here and here. There's bands, but there's nothing, there's no corner modes or anything. And now the way to connect these 4 corner states to the bulk bands at pi, we can again figure this out by using the chiral symmetry of this model, which I haven't even told you yet. But the chiral symmetry, and this is very much analogous to what we did in the 2D case when we looked at the mirror symmetric model in class A3. The chiral symmetry is sigma 3 tau 0 times h of kx, ky, kz is equal to minus h of kx, ky minus kz. Okay, so that tells me, and again, this is local in kx and ky, so it's local in x and y. So what it tells me is that if I have one of these corner states that moves upwards here, has to move downward here, okay? And now I have 4 of these guys. And if you go through the analysis, you'll find that there's 2 that move this way, and there's 2 that move the other way. So, and then there's these bulk bands. So what you basically have now is a system which has modes that are traveling on the hinges of the system, right? And as you go from one hinge to the other, the hinge modes, they reverse sign. So on one hinge it goes up, on the next one it goes down, then it goes up again, goes down again. And these are now protected. You cannot remove these hinge modes as long as you keep this mirror symmetry in the bulk, this diagonal mirror symmetry. You cannot remove these hinge modes. And also, since this is now a situation where we have spectral flow, we can basically forget about the chiral symmetry, right? So the chiral symmetry, similar to the transition from the Suschrieffer-Heger chain to the Chern insulator, where we could drop the chiral symmetry once we figured out how the bands connect. Here is the same thing for this edge modes, for the corner modes of the 2D system to be at 0 energy, we need the chiral symmetry. But for these chiral states at the hinges, we can forget about having the chiral symmetry. It's enough to have the mirror symmetry in the bulk. And okay, so that's basically that. And again, it's a bulk invariant that tells me, a 3D bulk invariant that tells me about these corner modes. So I can do to the surface whatever I want, as long as I keep this mirror symmetry intact in all surface manipulations. I cannot get rid of these hinge modes. Okay. So I have a little more than 10 minutes, and I have 1 page to go. So are there questions on this one? Okay, you're very tired. I understand that, but I would like you to switch on your brain for 10 more minutes. And the reason is that I'll switch gears a little bit, and I think this is very valuable because what you've seen so far in this school, and most of what you'll see for the rest of the time, is going to be exclusively on band structures and non-interacting systems. And I think it's important that we do not forget that there is also a strongly interacting equivalent of all the things that we say here. So all these topological phases, they also exist in strongly interacting systems where we cannot just draw band structures and understand everything. And for that reason, I wanted to quickly tell you about SPT phases and give you the simplest example in 1D of an SPT, and a simple example of a higher order or crystalline SPT. Okay? Let's see whether we can get that done. 10 minutes. So SPT phases. And it's more like an example. Obviously, I won't develop the full theory, but it's just so that you basically have the oversight of what there is and you know, don't think always in terms of band structures. So what I want to look at is a 1D chain where each side has a spin 1/2 degree of freedom. And the model that I'll look at is still exactly soluble. It's just not, you know, corresponding to a band structure, at least the way I present it. So on each side, I can act with the 3 Pauli matrices, and I'll just call them X, Y, Z. Okay? And I would like to look at the following Hamiltonian, and I'll call this H topo. And that is on every side I apply the operator X on the side I minus 1. I apply the operator Z on the side I, and X on I plus 1. Okay? So on this, I apply X, Z, X, apply here, X, Z, X, and so forth on every side, right? The sum over all of these products of 3 operators, that's my Hamiltonian. Now, the first thing that you should note is that all of them commute. Okay? So because Z and X anti-commute, but they come twice in the neighboring operators, they all commute. So, the ground state is just a state that is an eigenstate, a simultaneous eigenstate of eigenvalue minus 1 of all of them. And now I will also write a trivial Hamiltonian, which is the sum over I over Zi. Okay, so that's a paramagnet, right? So all the spins are polarized. This is certainly trivial. And now I'll tell you a symmetry that I choose to use, and that is a time reversal symmetry, which is given by the product over the set operators on all lattice sides times complex conjugation. And the point I want to make is that these 2 Hamiltonian are in different topological classes with respect to this symmetry. Okay. And so how do I see that? The easiest way of seeing that is by checking for end modes. And so let's say we terminate this chain, right? And we want to look for so certainly in the bulk this is all gapped, right? Because we have, you know, you see that since they're all commuting, the ground state has -1 times the number of these operators as an eigenvalue, as an energy eigenvalue, and the first excited state would be one where I flip exactly one of these guys, and then it's you know, the energy is higher by 2, so the ground state is gapped. Okay, and the same is true here, right? The moment I flip one spin, the energy changes by 2, so it's gapped ground state. And now what about the end of the system? And here I'll just give you 3 operators. They are Zx so this is the last side. So the product of Z on this side, X on this side, the X operator on this side, and the Yx operator. So the Y acting on this side, X on this side, okay? So these 3 operators, they have 2 things in common. The first thing that they have in common is that they all commute with the Hamiltonian, with this Hamiltonian. I'm talking about this one, right? They all commute with H topo. Okay. The second thing that they have in common is that they are odd under T, so they anticommute with T. Okay. And now what does that mean to have these 3 operators here? Well, it means that among themselves they obey the Pauli algebra, right? There's like sigma x, sigma y, sigma z. You know, that x here doesn't matter, right? So they obey the Pauli algebra. So what that means is that there needs to be a twofold degeneracy in order to represent this Pauli algebra associated with the end of the chain, right? And this twofold degeneracy is the topological end state. And now you can ask me, well, can I maybe sort of lift this degeneracy somehow? Then it wouldn't be topological. But since all the operators that could lift it are odd under T, I cannot add any of them while preserving T to the Hamiltonian. So that's degeneracy is a protected one, okay? So there is a twofold degeneracy at the end of this H topo. Obviously, for H trivial, there is nothing. It's just a polarized state. Okay, so did that sink in a little bit? Yeah, had a lot of time to think. Let it think. But it made sense, hopefully. Okay, so then let's do this in 2D and construct a higher order topological phase with that, in a similar spirit. And here again, so I'm looking at the 2D lattice. And I'll present, again, two Hamiltonians to you. The topological Hamiltonian I'll write in a little bit of a more schematic way. So I'll apply the set I operator to a side, and the X operator, so it's a product of X on the neighboring sides, on the diagonally neighboring sides to this one. So what I mean by this operator is that I apply Z here, I apply X here, 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 and here, okay? And then I do that on every lattice side, yeah? And so it's clear what I mean by this Hamiltonian? And so it's this operator, it's the product of 4 X's and 1 Z, and I apply that to every lattice side. And then again, I have the H trivial, which could just be sum over I, Zi. My time reversal is still the same one as over there, but in addition, I want to use a mirror symmetry that permutes, so I want to look at this mirror symmetry M, that the mirror symmetry is just permuting the sides. It doesn't do anything to the in the spin space. Okay? So M mirror symmetry. Okay. So so we have to do two things now. The first thing is we have to talk about the edge of the system, which I haven't done yet. And then we can talk about the corner, okay? So what can we do to the edge? There's two options. And one of these options is to basically extend this Hamiltonian to the edge in the sense that I put on the edge the terms that are set, so X set X. So if I have this edge, so let's see. So that's option 1. I put terms that are set X, X. Again, I can put this on each of the edge sides, and the operators commute with themselves. They commute with what is already in the Hamiltonian. So that's edge termination 1, and it is certainly mirror symmetric because, so it's time reversal symmetric, and it's also certainly mirror symmetric because, again, the only thing I need to make sure is that I put the same thing on this edge as on the edge that goes downwards, right? The second option that I have is to put on the edge, so that's another picture of an edge. I put operators X, X on the edge. Okay, so I put the product of X on two neighboring sides. And that is also fine with time reversal symmetry. And it also commutes with the Hamiltonian. So I seem to have two different edge terminations. But the second one is actually something special in the sense that, well, what will be the ground state if you just look at the edge? If you put XX on neighboring sides and you have a spin chain and you put XX, there's just the Ising model, right? It's like just the spin, depending on the sign, the ferromagnetic or antiferromagnetic interaction of neighboring sites. So if I put this on the edge, what will happen is that my edge will spontaneously break my time reversal symmetry. Okay, so so that is not good, and for that reason, so we always have to remember that topological phases are, there is this caveat, right? We need to, in interacting systems at least, we need to not only make sure that the Hamiltonian obeys the symmetry, but also the ground state should not spontaneously break the symmetry, otherwise there is no bulk boundary correspondence or anything of that. So this edge is basically forbidden. I thought this was colorful. This edge is basically forbidden because it's corresponding to a spontaneous symmetry breaking on the edge, right? So this is an edge termination I cannot use. And now with this edge termination, I'm in business. This will add basically another number of constraints to the Hamiltonian so that the edge gaps out. And then I can basically talk about the corner. So with edge 1, then I can give you 3 operators on the corner, and they are, if I have this corner, they are given by set x, by y x, and by just x. Okay, so there's 3 operators. They all commute with the Hamiltonian, and they are odd under the product of mirror times time reversal symmetry. So they are basically satisfying the same 2 conditions that we have over here. So they are commute with this H topo, and they are odd under mirror times time reversal. And so I cannot add them as perturbations to the corner of the Hamiltonian if I want to preserve this combination of symmetries, right? So what that tells me is that I have a localized degree of freedom, twofold degeneracy at the corner of the system. The bulk is kept, the edge is kept, and so this is also a topological crystalline phase, but this time it's an SPT phase. It's something that's, inherently interacting. You see that this is like a lot of spins that talk to one another here, so there's no chance, I guess, you can Jordan-Wigner this or anything. So this was just to show you that sort of not only in the realm of electronic band structures, but also in spin systems and strongly interacting systems, all these notions of topology exist, and many things carry over, but we have to look at them with different tools and with a different angle. Okay, so this basically is the end of my 3rd lecture. So questions? Mm-hmm. 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 Yes. So I think now one has to think about the sort of limits. What is the radius versus the correlation length and everything. But what you are guaranteed is if you have 2 surfaces which are gapped, then you'll have a gapless state, and they are sort of 90 degrees, for example, like in the case here. Then you'll have a gapless state somewhere between the 2. That's guaranteed. But of course, if you make this region between the 2 very large, this gapless state doesn't need to be in the lateral direction, doesn't need to be very localized. It could be as delocalized as your basically your edge, determined by your edge, by the radius, of curvature of your edge. But it would still be, it's guaranteed by the fact that you have these 2 terminations which are 90 degrees with respect to one another. Yeah. Exactly soluble, right.
So you would have, I mean, if you want to talk about, if you want to say that this is a representative of a meaningful base, then you would still have to check that, let's say, the Gaussian stuff is
Right.
at some conservation or something like that?
So the point is that you can now adiabatically, if you can adiabatically connect the bulk of this Hamiltonian to a bulk of a Hamiltonian that you're interested in, which might not have zero correlation length, while preserving the symmetries, then you're in business. So basically you can do this with some unitary operation, or some sort of finite depth local unitary, people say usually. So you do something that's that is preserving locality of the Hamiltonian, preserves the symmetry. If you connect the Hamiltonians, preserving the symmetry, then you're fine, because you can apply that same unitary operation also to this simple end state that I constructed here, and you'll get a more complicated end state, maybe that's somehow exponentially decaying or something, or where this operator, rather. It's not really the state. It's not, you can't think of an end wave function because it's not like a single particle picture, but you would then take, for example, this X operator. You come with your complicated unitary, and it will be a more complicated operator, but the weights will decay on the side. So in that sense, these fixed point Hamiltonians are a good starting point to think about the phase, but whatever you can adiabatically connect to them obeys the same physics. Yes. Yeah. It's unique. Then it's unique. There is for each. So this guy, there is only one sigma z for each lattice site. And so there's no way, there's no sort of identity like in the toric code that would, But it's short range, right? Yeah. But you almost said it, right? The entanglement is, here it's short range, and the toric code is long range, right? Or there is a topological ground state degeneracy on the torus. Well, no, I think you have to stare quite a bit if it's sufficiently complicated. I mean, you basically have to see whether out of these stabilizers you can, build an identity. Here it's simple to see it, but if maybe it's harder for other systems. So I don't know. Yeah.